Could you start with your first round of questions, please?
Yes. Do you hear me?
Yes.
Thank you, Salva, for the very nice presentation.
You're welcome.
It's a beautiful collection of results.
Thank you.
My first question is about your algorithm that computes a 1 plus epsilon approximation of minimum vertex cover. Let's say unweighted.
Okay.
This algorithm satisfies that the approximation holds an expectation, right?
Yes, the randomized, true.
Yeah. So the size of the minimum vertex...
not quite. The expectation is on the size.
Yeah.
With high probability, you can, on the rounds, you can get this. Yes.
Right. So the size of the minimum vertex cover is 1 plus epsilon far from the optimal only in expectation, right?
Yes.
So my question is it possible to obtain this guarantee with high probability? And if yes, how would it affect the runtime, if at all?
Okay. So if you can do this with high probability. So this is based on, so remember our general framework, it was a clustering technique, right? So we adapt a randomized clustering technique to our setting to achieve this special clustering. Okay, we use MPX, if you are aware of this algorithm.
Yes.
Yes. So MPX shows that you can get a clustering that is of diameter, low diameter with high probability. However, what MPX shows is that the number of intercluster edges are only small in expectation. And the idea is that they show that the probability of an intercluster edge, being an intercluster edge, is constant. So now you can argue the number of intercluster edges are a constant fraction of the total edge set, right? So you want to prove this property with high probability then, for us to get something with high probability. And not just this property, actually a more stronger property. You can use MIS to show that the probability of being an intercluster edge as well as being an edge one hop separated from the middle is also constant. So this whole set of edges now is a constant fraction, right? But this is only true in expectation. And it doesn't seem one can show it with a high probability. There are results that give a clustering with a high probability, low diameter, clustering which partitions the whole node. It gives you a clustering with low diameter such that there are some nodes outside that are small with respect to the whole node set. However, can this work in our case? So is it enough to show that if nodes are small outside, you can compute? So the idea is that why do I want a small number of edges in the middle, intercluster edges? Why do I want them to be small? So that I didn't, yes. So we said okay. Then this would admit a low-cost vertex cover. And the idea there is, so there's a pre-processing step that I don't include. We can compute easily a maximal matching. And what we actually show is that not just the number of edges in between is small, but the weights of the edges in between is small. So if you compute a maximum matching, you can then give a weight for an edge to be 1 or 0. And then, in between, you have a small set of matched edges, right? So now if you take both endpoints of the matched edges, you've covered everyone with a 2 approximation vertex cover, right? Because taking both nodes of a maximum action is 2 approximation. So the idea is, if you have a clustering now, go back to what's known right now. If you have a clustering with small edges, small nodes outside, can this help us gain a vertex cover for the outside world? Can we cover all of the edges outside, knowing that you have a small number of vertices outside? For the weighted case, at least, not necessarily, right? So you want to show that, because,
You already, in the deterministic case, though,
yes.
right?
Yeah,
The expectation the size is not in expectation, right? But there it's just that the runtime is polylog n over epsilon, right? While the
Yes.
randomized case, you do better. The complexity
Yes,
is better,
because we
right?
can, yeah.
That's why I was just wondering whether maybe, because like if you allow yourself to spend polylog n over epsilon, right? You can achieve this, as you show in your thesis, right? I was just wondering maybe if there is any way or any idea one could pursue.
I mean, the bottom line, if you can show MPX with high probability, yes, you can.
Right. I see. Or something.
This is already an open question, right? Even for that clustering thing, it works in local, not congested, not even on power graphs, because we adapt the whole MPX to power graphs, and there are other things. So there are other things to take into account. Yes.
So the congest is a good. So there is this generalization to high probability for MPX.
Yes.
But yeah, I mean, okay, you need maybe slightly different conditions here, and so you have nodes have weights. You have to make sure that the total weight outside clusters is small, and all should work. But probably one should go over the math.
Yeah.
There is this paper by Iran and somebody else at DISC 2 years ago or so, where they actually do it with a very small overhead, like polylog n 1 over epsilon overhead. But it, it probably works for weights.
Yes, but we want to make sure these key properties are satisfied. So we want to adapt this so that.
Yeah, so it probably works, but one would have to go over the math.
Exactly.
Yeah, it's there is some work needed there, right?
Yes.
Yeah, I see. Should I continue?
Yes.
Yeah,
okay.
sure.
You can continue as long as you want.
Okay. So, okay. So as you say in your thesis, there is this lower bound for computing 1 plus epsilon approximation of minimum vertex cover, right?
Yes.
Does this lower bound hold also if you only want this approximation to hold in expectation? And if not, is there any lower bound known for this case?
I mean, it holds for randomized algorithms. So we show that in randomized with high probability, if that's what I remember. Yes, because this is based on the previous lower bound. So where is it?
Yes, from Suomela.
Yes, which there they already show.
Yes,
this one here. It's Gus and Suomela. We just
extend.
Yes, and there they show there's no randomized algorithm that solves this problem faster than log.
Right.
In local model, yes.
Right, but the lower bound, does it hold if you only want the approximation to hold in expectation?
So you're relaxing the thing. Okay.
And if not, I don't know. I was just wondering whether you have any idea if there is.
I mean, I'm not sure because they reduce it to another hard problem, which is now I'm remembering the cut, a special problem, a special cut problem. And yes, continue. I interrupted.
No. I was just saying whether you have an idea, whether you know if there is any such a lower bound for this case specifically that holds if in the literature. I don't know if you have any idea.
I'm not aware, but this would be interesting because what we show is an expectation. So yes, we then can show tightness. Yes.
So the lower bound is not an expectation lower bound? I thought it is.
I actually don't know. I'm really I'm asking because I really don't know.
Yes, I don't remember.
Maybe it is. I don't know. Maybe it is. I don't know. Maybe it is.
So let me ask, I mean, you can continue, but let me ask this differently because I think we can figure this out. So for what kind of graphs is the lower bound stated? Do you remember that?
Yeah, I remember you have these graphs that are.
So what is
expanders?
Expanders, yes, but what's the?
They have maximum degree MO3.
Right, 3 regular graphs, so maximum degree 3.
Just that they are.
So shouldn't you have enough independence in 3 regular graphs that any algorithm which works in expectation also works with high probability somehow by lying a bit about n or so.
Intuitively. Intuitively,
I
yes.
think
And you have even more properties on this. I remember it's balanced and so it's oriented also. Okay.
I'll let you continue.
Okay.
Yes.
Okay, so probably this is well, good to know. Good to know. Okay, now regarding now the deterministic algorithm for 1 plus epsilon approximation of, let's say, unweighted minimum vertex cover. If I'm not mistaken, this algorithm uses network decomposition, right?
I mean, this clustering is based on network decomposition or
No,
low
I
diameter
mean the
cluster.
deterministic one uses just the network, right? The Rojan and Ghaffari, right?
Yes, so this general framework adapts Rojan and Ghaffari's. Yes.
Right.
Yeah.
So over the years, the complexity of network decomposition has decreased.
Yes.
So does this already directly imply some
A better runtime.
better,
Better runtime for
your or is there any one needs to, I don't know, it's not something that you directly get, but one needs
It's
to
not
do some
something you
work?
directly get, but it's easy to adapt. So if you recall the Rojan and Ghaffari algorithm,
Yes.
you have read, okay, just to answer your question, probably yes, it can be. So the constant here in the poly that I don't mention is 7 or 8. In the congest, it can be probably shifted down to 5. Because we really need the idea that we want to show that the weight of the edges that are not clustered, so outside, is small. And for that, we use Rojan-Ghaffari idea where you have these red and blue proposals. So red nodes propose to join a blue cluster if its weight is small with respect to the total weight. So what we adapt is essentially just the edges, the weights of the edges incident to those red nodes.
Mm-hmm.
Are they small with respect to the total weight of the cluster? So that's the adaptation that we do with some other minor adaptations also. So if any other network decomposition result allows you to argue in a similar way, not just on the one hop, so we also use the Rojan and Ghaffari on G squared, so they prove it, the first paper proves on a power graph, right? So you want to also show similarly for power graphs, if you can do that, then yes. And the best known network decomposition is, that I know, in the state of the art, is gives you something close to log squared n, which is based on a de-randomization of MPX. So using our local rounding also. However, again, if you can show that, what they show is that you have small number of nodes clustered, right? But it doesn't seem obvious to show that you will have, you can define edge weights and then you can adapt this to show that a small fraction of the edge weights get unclustered. So it's not clear. If one can show that, then yes, you can improve this to log squared runtime. But yes, this is a nice, actually, a research project for a student. Yes. I gave a lot of open problems, so I think this is one of them.
Oh, really?
I think, yes.
Okay, sorry then. I missed it, but we thought about the same question then.
Yes.
Yeah, I mean, I can see how the first network decomposition algorithm is so beautiful and simple, right?
Yeah.
So it's nice to work with and it's nice to adapt, while maybe the latest ones are more, like, let's say, involved.
Are involved, yes.
Yeah.
Yes, true. Yes.
So, staying always in the minimum vertex cover theme topic, is there any way to improve this epsilon to the power of 3 in the randomized algorithm? Or would there require totally different techniques?
The way it is now, doesn't seem one can improve it. So again, the idea is based on MPX. So for that, you need log n over epsilon. That's one of the
Right. One.
powers.
Yeah.
We adapted slightly, but it can still work in log n over epsilon. And what we need is, so we do the clustering. So now we're looking at the cluster of diameter log n over epsilon. And there, the expensive part was to compute this good approximate vertex cover, right, on those low diameter clusters. And for that to happen, we have a technique that that builds on a classical theorem called Kunish's theorem, where it can kind of produce for you a vertex cover, a good vertex cover, given that you have approximate matching with some property, okay? So you can get roughly the same approximation for the vertex cover if you know there's a constructive way to do so, if you know how to achieve an approximate matching with this special property. What's this property is that, well, you have short augmenting paths. You don't have short augmenting paths. Okay, so this cube comes from here because we want to be able to give our clusters a matching with no short augmenting paths. And short augmenting path, I can define it 1 over epsilon. Okay, so roughly big O. So to achieve such a matching, deterministically is not known. Randomize, it is known. It's based on an algorithm by Lotker et al., where they essentially simulate a sequential algorithm, a classical one, Hopcroft and Karp. So you go through the lengths of the short augmenting paths sequentially, and you try to augment on a maximal independent set of those. So you're augmenting on disjoint path. So now you have no short augmenting paths of that length, and then you move on, right? So now you will have to use this algorithm. So we use this algorithm. This is randomized. Mm-hmm. And from there you get the epsilon cube. So you have to first, so if I want to explain the powers where they're coming from, mm-hmm. It's on, you're going, each step, each short augmenting path, and try to find an MIS. So now you already have the 1 over epsilon, right? So 1 in the power. And for each step, you want to compute an MIS of a disjoint set of these shortest augmenting paths. And you want to do it distributed. So that's not easy. So what they do is, what can be done is that to compute, define a conflict graph where you can think about each augmenting path is a node, and 2 augmenting paths are adjacent, so they share an edge. So now you want to compute an MIS on this conflict graph. And in there you will get some congestion because they apply Luby. So what we talked about Luby, essentially. So they make it distributed here. And so there's a way to give every augmenting path this random value 1 over degree, for example. But for that, you need to know the degree. So you need to do the path counting method where each node needs to know how many different augmenting paths adjacent to, so that this is what it means to know its degree in this graph. So you have the path counting method already gives you another 1 in the power, so now you have 2. Or if you want to apply Luby, you're going to have at least this 2 in the epsilon. And now the third power, so it has to do with the application, which I'm not able to remember the step because of congestion.
I think it's because iterating over the path lengths, isn't it?
Yes, that's I said this is
okay. That's
coming
the one.
But there's another third.
Okay.
I'm not able. I think it comes from the congestion. The number of different. I mean, the degree in this conflict can be very high. Delta to the power d. D is like the length of the shortest augmenting path, and then you would have to send log d times log delta. So d is, you can think of d as 1 over epsilon at most. So that's another
I think you just
One
said
and
it.
the
Yeah, it's
power.
it's delta to the 1 over epsilon. If you take the log, you get
Yeah.
another 1 over epsilon.
Yeah, that's
Or
another
just the
thing.
loopy running time. Yeah.
Yes, that's another of the power.
Yeah.
Yes. So getting faster meaning getting either solving, Hopcroft Karp, simulating distributed faster,
Mhm.
or
totally new ideas, maybe.
totally right.
Yeah.
I mean, yeah, it's very interesting because then you can achieve a tight bound, actual tight bound. So yeah.
So if I'm going, I would go to a couple of questions about the local rounding, but I don't know if Fabian would like to ask questions about minimum vertex cover now or later. Otherwise, I change topic.
Well, let's continue in the first round, and then we'll come back to you later.
Okay.
About that.
So let's change topic and let's talk about this local rounding technique that, as you already said in your presentation, it has been used a lot, right?
Yes.
So my first question has to do with one of the open questions that you mentioned, that is about like where to apply it and what other problems to apply this, right? And one specific problem or family of problems that come to mind is the 2 beta ruling set that are a generalization of MIS, right? So where the larger is beta, then the easier the problem becomes. So in particular, this problem, the 2 beta ruling set problem, requires to select an independent set of nodes that only needs to satisfy that nodes outside the set are at distance at most beta from a node in the set. Okay, so 2-1 ruling set is an MIS, while 2-2 ruling set is easier.
Yes.
So do you think it would be possible to use local rounding to solve 2 beta ruling set with a runtime that decreases as a function of beta? Because now with the increase of beta, the problem becomes easier. So for example, can we achieve through local rounding an algorithm for 2 beta ruling set with complexity log n times log delta to the power of 2 over beta? This would be a nice
generalized result.
Like complexity to achieve. Or could it be an interesting follow-up question to study, like a specific interesting? Do you think it's a nice follow-up question to study? Like, I personally don't know the answer to this, so just so to say, I mean, I'm not.
Okay.
But if you are maybe more familiar with rounding, maybe I don't know, something comes to mind or some.
Yes, maybe. Okay. The only thing that's crossing my mind is, so we have this. There's a result, like if you have on pass, if you consider pass now, let's just consider simple graphs, where one can compute a special set of nodes called light nodes that make up a 2 beta ruling set.
On paths, you said?
Yes, on pass. It's, yes.
On paths,
Yes. Let's just
log star end problem. So.
Yes, but I'm just making it simple so that
okay,
one can, maybe I can argue in a more general fashion afterwards. So because there, the 2 beta ruling set is based on an MIS of the power graph. So choose a subset of light nodes, say special nodes, and then consider the power graph. So that on this special set of light nodes, such that if what power like start with 2 and then increase. So if every 2 light nodes are away by 2 hops, connecting with an edge and so on. Yeah. And then if you compute an MIS on that, and repeat, so increase the beta with time, you eventually get a ruling set, which is 2, if I remember, 2 1
But
over
this-
alpha. So my idea was, can we reduce the problem to MIS? On a different
like doing things on power graphs would increase the runtime, right?
Yes, exactly. So
Yeah.
it makes things worse, but
Yeah.
So if you know of a simple randomized algorithm that solves your ruling set problem, then probably you can extract some quantity of the solution that you'd like to preserve there, and then we can try to fit it into our rounding framework and de-randomize it. So that's the go-to way for the local rounding if you have simple randomized algorithms. Doesn't have to be, but I don't know if there is a randomized algorithm that solves that quickly. Another way is to just use this frame, because this is how you solve MIS, right? We de-randomize Luby. Luby is
Right.
So where the fractional values that we talked about are the sampling probabilities, for being marked or not, and then you define this quantity that you like to preserve from Luby, which is representing the number of the expected number of removed edges per round in Luby. So that's something we'd like to preserve because it tells you per Luby round, you lose a constant fraction of those, and then you can repeat log n. That's where the log n is coming from. So if you can do something similar with your problem, then easier potential, so with easier phi, where you don't have to repeat log n, because this is the log n, where it's coming from. You repeat this randomized procedure log n times, then probably, yeah.
Yeah, it's this family of problem is quite it's a generalization to MIS, which would make it maybe a good candidate for, but still, I mean, I have thought of it sometimes.
So
but-
just to add, I remember Alkita and me
Yeah,
failing
exactly.
at it, right? We tried.
So I thought maybe let's.
And some others.
Yes, exactly. So it's a bit frustrating, right? Because.
I mean,
But yeah, I don't know how to solve it, but yeah.
It needs a
I
paper
would-
and a
I
pen
would
and
love
some
to see-
research of the state of the art, probably.
Yeah, I would love to see this problem solved. Let's put it this way, yeah.
Okay, nice. yeah.
Okay, on a more generic question regarding the local rounding technique, would it be possible to define some family of problems and prove some meta-theorem of the form all problems in this family can be solved in order of log n times log to the power of 2 of delta many rounds deterministically? That is, what I'm trying to ask is, can we find some generic properties such that all problems that satisfy these properties can be solved via local rounding in this complexity?
I mean, if you can reduce this problem to MIS quickly, then yes, because all of these 4 problems here, for example, in the local model, they attain the same runtime because, okay, you can see it as a reduction to MIS, and for MIS we can solve it for local rounding. I mean, that's a silly way of answering, I know, but
my question, as you can imagine, my question is there something, some property that are more like, let's say, fundamental that makes it so that this local rounding technique would give some results, like can be applicable, like for example something, I don't know, some property that, let's say,
I mean, it's very unified. So the cool thing about this technique is that this phi, this fractional quality, this potential that I call, it's not necessarily have to represent the value of the solution, like we do, like the size of the independent set, or so on. It's very general, so you can represent any key property of the problem that certifies that that your solution is going to be good. You can represent it with this phi. So this is how general it is. However, on the condition that you need to rewrite it as this linear combination of pairwise interactions. If you can do so, then it works. Or give a pessimistic estimator of whatever you're trying to bound as an expression, as this expression of that format, and then work on that. So that's already very general, I would say, and appealing. And this is why many of these problems are working. Like there's some quantity that I can represent it like this in that format, and then so that's already I don't know, it's general, but if I understand your question more,
there are other problems that they solve via rounding, right? This partial coloring. This paper appeared in maybe Sirocco. The solves partial coloring.
effective, you mean?
No, there's this paper on partial coloring, this
Yeah.
K-partial thing.
Defective,
Yeah.
the same as defective.
No, it's the
In some cases, it is the same.
yeah, it's related. So it's basically you have a parameter K and you want at least K neighbors with a different color. And they have some log square K log n algorithm, I think, using rounding.
Right.
Something like that, right?
Yeah. Right.
This was
also,
this student of Pierre, right?
Yes. And also, I
yeah.
remember that we also had some results about arb defective coloring with you, Fabian.
Arb defective.
Yes, never published, but yes.
Never written.
Because it's very simple.
Yeah.
Yeah, but that's all the
But
same.
I mean, I
right?
just wanted to say, yeah. What did you say?
It's always the same kind of. But yeah,
So now you're focusing on special graph problems. I mean, family of graph coloring.
Yeah, I
Yes,
guess this was the
problem.
question, right? Can we say something more generic than this problem works and this problem works and this other problem works? Can you?
Like what makes
And
it
if we had the answer, then we would have published it. I know, but it's
I mean, that's the big question.
No,
Where else
I
can it
mean,
be?
there are all these examples, right, for which local rounding works, right? And there are also recent examples, right? This partial coloring thing, the never published, so you never knew about this. Arb defective coloring is another example, and then MIS, and then
And network decomposition also.
yeah,
The fastest known, yani,
right.
considered. Yeah.
So
So
my question is like, is there any property that we can extract? And like that maybe all these problems satisfy, but that is a bit more generic that says, and try to prove a meta theorem saying, any problem
that would be very nice.
But I mean, yeah.
I mean, the other techniques like network decomposition, do you even know of a meta? I mean, anything that can be solved in the standard way?
Well,
Network decomposition, if you consider that as a meta?
Well, no, I mean, you can say, I don't know, any problem that satisfies that you can, I don't know, you can express it via local constraints, let's say locally checkable problems, right?
Yeah. Yes,
This is a family of problems, and this family of problems is defined via some generic properties, right? And you can say any locally checkable problem, I don't know, can be solved in log star n rounds by some generic algorithm that solves them all in log star n.
So we look at, so if you want, you look at graph problems that can be defined over labels. So solution would be an assignment of labels subject to some constraints that you want to preserve. That would be more or less.
Okay, so I guess we're like now over the hour, so like maybe we move on with Fabian as next.
But the question she asked is very important. So
Yeah, sure.
It's like breakthrough. It would be a breakthrough result in the field. So,
But I have one last question, if I may. It could
Yeah,
should
go
be-
ahead with one last question. That's fine.
Okay. So, what would fail if you run your algorithm for clustering trees, the one that is that runs in order of log star n over epsilon? The clustering trees.
Clustering trees.
Yes.
the independence.
What would fail if you run that on general graphs? If you have a fast answer to this, genuinely interested.
I mean, it's tailored, well, for general graphs, I mean, because it's in congest, then there are steps that you run to congestion
Even in local.
in local.
Yeah.
In local, it works for planar graphs, for example, but where it can fail. I mean, this is a result in the local. This result already exists for local in planar graphs. So this is what we adapt. We adapt it to congest.
Right.
Right. To work. And the clustering is, well, they use bounded they use that the arborist is bounded to be able to, yes,
I
because
see.
they want to do a coloring on a rooted, so they tree where
Bounded arboricity is something that
helps.
That
Yes.
require. Okay.
Helps. If you're general, there are all of these steps that are very creative and clever, and I don't see a way to even say something. It's very tailored to this problem. So
Right, I see.
that's why it's not easy to extract.
see.
But
No, I just wanted to know. Like,
Yes,
okay.
okay.
Thank you. Thank
You're
you very
welcome.
much.
You're welcome.
Okay, thank you then, Fabian.
Okay. Let me start with some more generic question. So you list a lot of open problems in your thesis. So are there any particular ones that you think are, so maybe if you have to pick one, which is the most promising one to look at, what would you pick?
I mean, other the one with improving the power in the poly for the minimum vertex cover problem to get a close to an optimal solution. Like you can, I would pick set cover, where, so one of our results using local rounding was that it gives you this log S approximation.
Yes.
O of log S approximation in polylogarithmic time. But so there's a greedy sequential algorithm that gives the 1 plus 2 ln S, if you want the harmonic thing, approximation. And getting better than logarithmic sequentially is hard. And that doesn't mean this is going to be the case here in distributed, but it's just
So improving the constant in the approximation.
constant, because I don't tell you what the constant is. The constant is very high. And we didn't care about the constants when getting this result. So in the discussion, I parameterized the whole problem because the constant the whole problem is governed by the analysis and the algorithm is governed by some small set of parameters subject to some constraints. So I was able to parameterize the whole problem, and then you want to optimize this expression, this approximation ratio. I can write it as an expression as a function of these parameters subject to these constraints. And you end up wanting to solve some nonlinear system, non-convex, which I'm not sure if there's a solution. I mean, it's non-compact, the region of that we're looking at, but there's hope to improve on this constant. So I was able to improve from, what was it, 200? We give something in 200. This was a 200. Yeah, I mean, it's theory world, so we sometimes throw them to the big O. Yes.
200 is the same.
Yeah.
Yes. So with the parameterization I give, I was able to bring it down to 21. And there's even a better way to, which I don't mention in the discussion, this 2, so can even be improved. So it can be even be improved to 2. So the algorithm gives, it's based on a de-randomization, a randomized algorithm, right?
Yes.
Where the randomized gives you a 1 plus 2 log.
No 1 plus. There's not, where's the 2 coming from?
You saw the 2 approximate fractional cycle.
Oh, but the fractional you can solve 1 plus epsilon.
Exactly, that's what I'm trying to say. So this, the way I do it can be even improved further if I choose 1 plus epsilon or constant better than 2, because you can even solve it for any constant better
Okay,
than.
but yes, so you answered the question.
Yeah,
This is,
interesting.
so it's good that this is
This
the
would be
problem we actually have a master student working on the next semester.
This constant?
Yes.
That would be cool. Because,
It's- you know him. It's Dennis Atalay.
he's here.
He's here. Oh, yeah. Nice.
Were you successful?
Okay. So,
But the goal is to achieve the same approximation as the sequential gradient. So there it's 1 plus 2 ln. So also that.
so let me also then ask in the other direction about your open questions. So are there problems which are particularly hard and where you really need kind of some very non-trivial ideas to make progress among your open problems? So
Okay. Yes, this major open problem for vertex cover.
sure, yeah, vertex cover
For general
below
graphs.
2 where we know that
So better than 2, what I mean is better than by constant, not because our result gives better than 2 by low orders that vanish as the graph grows larger. So 2 minus 1 over n, for example. That's not interesting for me on large graphs. You want. So that is.
so I guess there is this area where we can go below 2, which is still polynomial times sequentially, right? This 2 minus log over log, which can be solved by STP.
Exactly.
But even making that distributed might be hard. But
That's-
and then we have to go to the range where we have to exploit the distributed model and use
Yes.
exponential computation locally.
Exactly. I would say I would follow up. Okay, let's not talk general graphs. Let's talk regular graphs. Because in sequential setting, to solve this major problem that I'm just talking about is reduced to solving it on regular graphs. There's a paper for that. So there's a reduction, polynomial reduction there. So even here, getting better than 2. So near optimum solution for vertex cover for regular graphs is not known. And sequentially, if you can do that, then you would solve the general case. Here it doesn't have to be, because the reduction is not necessarily going to be efficient in our setting here. I'm not sure. But that would be a hard question, I would say.
Okay, sure, I agree. Yes.
Regular is simpler. So even this general framework we saw, remember, okay, I mean, it works for general graphs, right? So this clustering technique here, right? This works. This doesn't have to be bipartite. The only case why we wanted bipartite is efficiency because of this thing here. We compute good approximate and time linear in diameter, right? So this problem of general graphs reduces to solving it on graphs with low diameter. Regular, not the case necessarily, because I mean, if you give me a cluster of a regular graph, it doesn't have to stay regular. So for regular, the problem is now reduced to solving, better than 2, near optimal, in polylog n. So if you can solve in polylog n, is good enough for regular graphs. Yeah.
Yes.
So it doesn't give you any advantage for regular. That's what I wanted to say. So Regular is not easy. Even with these STPs and the LP,
Yeah, the hard instances.
the hard instance, yeah, they call it the core, the hard instance graphs, yeah.
Yes, that's where the half integral solution is trivial, and
Or
all the difficulty is going from half integral to integral, right, for vertex cover.
Yes.
So let's talk a bit about independent set, maybe. So you have these algorithms which basically give 1/delta approximations, or roughly 1/delta, right?
Yes.
And then you mentioned this as one of your open questions of pushing a little bit and maybe going to, say, 2/delta. Right. Getting a constant factor above this 1/delta approximation.
Which approximation are we talking about?
Well, okay, you mentioned this as an open problem, at least for weighted. You say that for unweighted, we have a solution.
For regular graphs?
No, for maximum weight independent set.
Yes.
You want to get the 1/delta. So 1/delta approximation, we know.
That's the result.
And now you want to get to beat this by a constant factor. What can you say about this?
Yeah, that. I mean, this is.
So can you remind me what works in the unweighted case?
Yes, you have a greedy algorithm actually that gives you the 2/delta, and even better.
So
2/delta plus.
but this you can make distributed?
No, I don't know.
Okay.
I don't know because this is the minimum greedy algorithm, where essentially it's very simple, and it gives you such an independent set with other good properties that are used. Just pick the minimum degree node, remove it and its neighbors and recurse. So it's an MIS, yes.
Okay, so you do an MIS where you always pick the minimum degree node among the remaining ones.
Now, yes, and yes. So these are the non-sequential. I mean, this greedy has a lot of. There are a lot of papers that analyze how better to optimize this constant. There are a lot of the papers that give you improved constants, and the best one was delta. So it's close to this.
Close to 2/delta.
Close to 2, yes. Better than that, even sequential, we don't know.
Okay.
So
basically, okay, this version of MIS beats general MIS by factor 2.
Yes.
That's what you're saying.
Yes.
Okay. Any chance we can make this distributed?
I mean, there's an alternative way of doing this algorithm. They use it in their paper, the Magnus paper that's titled Greed is Good, where they try to find an MIS of a special nodes they call critical nodes, and those critical nodes you can get them via local property. So you can do it locally, yes, distributed. But what's hard, what I don't see how to do efficiently now is that they want to compute an MIS of these nodes, and they can be far away. I mean, they show that one of their properties that they can be at a far away distance from one another. So MIS on this power graph of, where any two critical nodes share an edge now. So it's a power graph with a higher power now. So doing an MIS there is what you are then asking me to do if I want to make it distributed.
I see.
This greedy algorithm, and for that it's not easy.
But this graph is local, so you could in local it would work. Is the problem just congest, or it also not work in local? Okay,
yes. It's MIS on a power graph where the power can be diameter.
Okay, yes, then
so
not local.
That's local. So yeah.
So how does so now I have no idea. I'm just making this up now. So this greedy algorithm that you describe, I guess, means you always take the minimum degree of the remaining graph and add it to the independent set. So what happens if you just initially sort the nodes by degree and just process them by increasing degree? So you start with the smallest degree, but you always look at the degree of the node in the original graph, not in the remaining graph. Does this already also beat 1 over delta, or does it not? Has this been looked at?
I don't think so.
I mean, maybe there's
So you want to stick
maybe
to
there's also an easy way. Yeah, maybe there's also an easy way to show that it has to fail, but I don't know.
Maybe you have counterexamples.
Now
where
asking the
this-
question, it seems like the question is constructing a counterexample.
Yes. You can just.
Let me stop for here and just give some others a chance to ask a question if they want.
Yeah, I can. Okay, thank you.
Yeah.
So thank you for a nice presentation. And after, obviously my colleagues want to get some research paper out of this defense.
That would be
Asking the most generic question, which is, what problem didn't you have solved and how can you solve it? Yeah. So I'm here with an agenda. So you are working on making randomized algorithm deterministic, this way. And I'm working on convincing people like Armin Biere to put a circuit in the processor which produce random bits.
which produces.
Random bits, that's something we need for decades, so that we have. So can you make the case why randomization is a good thing for me? So, and convince him that he builds a circuit which produces random bits, or because you're working on the opposite direction, you de-randomizing, obviously with unified approach. Do you know in
At
your,
least for this problem or randomized complexity, if you notice, they're faster.
it's faster, okay.
Oh,
By a factor of log
a
n
lot.
times 200.
There was a gap. I mean, there's
Yeah,
also this. There's also results that
And I
LCLs you have a exponential.
I looked it up. How large does a network have to be that log n is larger than 200? So that's it's not the number of atoms in the universe. It is the number of atoms in a small galaxy.
Okay.
So it's not too large, obviously, even for a petition, I guess. Okay, but that's upper bound, I think. So you showed you have a certain bound, randomized algorithm, and then your upper bound, your de-randomization adds a factor of log n. Can you lower bound it?
No,
That you can say, okay, there's no way that the deterministic algorithm is as fast as randomized.
yes. I mean, there are results that shows
Yeah, can you name some?
LCLs.
Hmm?
The LCLs. These are locally checkable
Yeah.
problems. So problems like,
And what,
coloring. Maximal independence set.
and what's the gap?
Exponential.
Exponential.
Yeah.
Okay, so that's
between
good
randomized and
argument for,
deterministic. Yes.
that's a good argument to have randomized algorithms. Now, what would you recommend if you want to do this in reality, so this algorithm? Yeah, so obviously you would not recommend to use your algorithm.
No. At least not the set cover. It's
Yeah, so but if somebody comes up and
21.
wants to solve resistive algorithms, what should they do? Maybe some trivial solution is good enough?
trivial solution. What do you mean by trivial?
Yeah, so what should they do? They're sitting at the program and asking for you for telling what to do.
I mean, if your system is not large enough.
Let's say 1,000 nodes or something, 1,000 node network, not too large.
I mean, the thing about these distributed algorithms, they're ideal. They're in an ideal setting, so we really don't care about the local computation here.
Mhm.
So there's this thing we only care about. You can cheat, you can solve NP-hard problems in here, essentially, by
Yeah,
selecting.
he's solving NP-hard problems all day. He starts in the
First-
morning and he eats one NP-hard problem and he thinks about p-space hard problems. That's what you do. That's your typical day. So you would actually collect it at one node and do exhaustive search, client server. And,
That's a trivial solution
and,
for
yeah,
you.
that's the thing that you would recommend for you.
Your diameter is not large.
So
Good.
yeah, I also noted that you have a chapter which is called applications, and
Oh, it's applications that look around it.
okay, we have a lot of fun here, obviously, which is applying this to other theorems and
Yes.
doing this. Okay.
But these problems do have applications in real world. And okay, I shouldn't talk.
You started it. So what are the real world applications? I didn't ask.
For example, I don't know.
So, okay. Yeah, I saw also the introduction, but I didn't want to ask that generic question. But you. Okay. So did
Yeah, let me go. Thank you. The same direction, of course. So I need to explain, like my last university, I was considered the most theoretical person here. I'm obviously not. So if I look here to the right, and always had to defend like why my theory was not practical. Right now, you are going to defend to me why your theory is important. Okay, but I'm not asking the generic application question. Maybe another one, because I know there's like this. There's Yuka in Helsinki who kind of reaches out to me, but there's more general question behind this. For your algorithms, literally when I do theory in algorithms, actually I don't trust any theorem before I have not implemented it. So I could ask this question, but I'm not asking this question. And then even implementation is not enough. I would actually test it and run it. And then after sort of like a long time, I figure out, oh, my theory is broken, right? So this is like usually what happens to me. And how do you do this, right? So how do you make sure that your theory is correct? I assume without implementing it. Yeah, but
Mathematics.
yeah, exactly.
Not
But like, what would be do you know like about methods how you could sort of like first part is get that your algorithms are correct, right? Somehow convince yourself sort of, as I said, I'm implementing this stuff and check it and then see whether it works. And maybe this and this is actually a very crucial thing, like that it's like as fast as you claim. Like how could you empirically kind of show this rate? Is there an empirical way to sort of measure that this, yeah, my algorithm actually has this complex?
There is this.
Maybe the first one or second one, whatever, like that.
Yes. I mean, we do prove correctness of these algorithms. So.
Yeah, but as I said, like I just repeat myself. So when I usually do this kind of stuff, and then it's usually broken, or like there's always this corner case which you forgot.
Yes.
And
yeah, because for example, for these low bounds, you look at very small special cases where this theorem breaks, and then you say it breaks. So if you find one small thing that doesn't work, the whole theorem doesn't work. So usually that's what
I'm asking more: is there a method, like a scientific method, which you could now use to get sort of more confidence?
Yes.
In that your formulas are correct, like both sort of that the algorithm is actually working right correctly, and then second, it has this complexity, like maybe some empirical method, maybe some other method.
What does empirical mean?
Well, empirical method is implementing it and just running it and see whether it's really sort of like not exponential.
I mean, usually.
Or do you know, like other people are doing this, or?
Yes, they do with parallel. There are some parallel programming where they do implement these algorithms. Now, I didn't have much contact with them, but they do what you want. So, Yuka and his group also. And there's also this with the fixed point thingy about the lower bounds. There are also ways to check lower bounds of problems.
Like empirically, like, or?
Yes, empirical, exactly. And actually, the partner of Al-Qaeda was a professor.
Elimination?
Exactly, I forgot the name. Yes. So there they can show lower bounds for problems that you can write in a certain format.
But you're not doing this, right?
It would be nice.
Okay, cool.
Maybe my next PhD.
Okay, great.
I mean, I'm coming from.
Of course, like I could go on and ask more questions in this direction, but I'd say let's do another very short run. So, like everybody of us, one more question. So please, Ms. Bayou, first.
Yes.
No.
Al-Kida,
Sorry?
No, we do one last round of questions because we have 5 more minutes.
No, I
And
have
so
no
everybody
further-
has one question which can be answered in 1 minute. That's the goal.
Yeah, no, I have no further questions. I only wanted to thank Salva about the discussion.
Thank you.
I also would close, but let me see if I have a short. Okay, let's go back to this rounding framework. Christian mentioned applications, which of course are applications to other theorems, applications in theory. So do you have any ideas, any suggestions where we maybe could use rounding? Any problems that come to your mind? It's not that I have anything in mind.
Cover.
Vertex cover.
That's if no one asked. I mean, why didn't I use it for vertex cover? I don't know how. That would be interesting. I mean,
Vertex
to solve the
cover,
big
yeah.
question, what I meant. Of course, you can use it for.
Is there a good randomized algorithm we could use for vertex cover?
I'm not aware of. I'm aware only for 2 approximate randomized algorithms, and better than that.
Yeah, so we can get the factor 2, right?
Yes.
And
That was the whole point. And understanding vertex cover even helps you understand the complex. I mean, if you can't understand the complexity of vertex cover, you can't understand the approximation complexity of set cover. So it's not that we look, okay, are they also in do you have real world applications, but maybe they are more special cases of more general problems that be interesting.
I guess, yeah, I mean, I guess one answer is use randomization and then the algorithms become much simpler, right? You need random bits. I guess I'll stop here.
Yeah.
Do you want to?
Actually, I have one question. So, I scanned for your PhD thesis, and am I allowed to show around your epilogue of your PhD thesis? Your epilogue? You added an epilogue in your PhD thesis. Am I allowed to show it around? Okay, thank you.
Yes, please. That was really nice. That was really nice.
Yes, I thought all of what you learned throughout your PhD has to be at some
Yeah.
point by someone.
Especially shopping part was very important.
You read that. I'm very happy. Thank you.
Yeah, almost excellent last words, but let me use the last 2 minutes for asking the audience if there's some questions here. Anybody? Questions, comments? Yes.
Maybe just like a very short follow-up questions on one of the questions that Al-Kida said. You had this algorithm for vertex cover with log n over epsilon cubed. And as I understood it, most of this came from the computation side of the diameter. Now, if you don't...
No. The approximate matching, getting a good approximate
Right.
matching, or just an approximation with no short augmenting path.
Exactly, inside of the
Doesn't have to be
clusters.
split.
So if you, instead of making an algorithm for congest, just do local, where you just basically brute
Work.
force a perfect solution inside of the clusters, do you immediately
Yeah.
improve it to log n over epsilon? Okay, nice.
So with this, I think let's thank the candidate again. Thank you very much. And now I have to ask everybody who is not in the committee to leave the room.
So everybody's who's on Zoom, who is not on the committee, I'll put you